Hey, it's Tony from Adafruit, and in this video I'm going to look at some interesting, more advanced topics with CircuitPython. So specifically some interesting ways that you can port drivers or code that talks to different hardware to work with CircuitPython. And I'll highlight a couple interesting things that we're doing with CircuitPython that might be interesting or worth checking out, even if you're more of an advanced user. So again, this is a little bit more of an advanced video, but I figured it'd be kind of interesting because if you're working on getting drivers and things to work with CircuitPython, like maybe I am, importing a bunch of our drivers to work with the new version of MicroPython that we have, then this will be very useful info, but it also highlights some cool stuff that even in the Arduino world you might find useful, or some problems that have been tackled there that we're starting to address with CircuitPython. So I'll dive in a second here. We'll go to the main view. And in this video specifically, we're going to look at the PCA9685 PWM driver. You can use this to drive servos, LEDs, even motors. I've done a whole video on this that I'll link to in the description below. But just remember, that video is for MicroPython, so you need to use the upstream micropython.org releases for that. And this video is specifically on CircuitPython, so we'll look at how I've converted that MicroPython driver to work with CircuitPython, and then just look at some of the differences and some of the interesting things that we're doing with it. So let's just kind of dive in and we'll get started here. I'll jump to the main view. Let's see, turn this on. There we go. And let's see, I thought I'll start real fast with just giving a quick little demo of the PCA9685. So the hardware I have in the upper right hand corner, underneath here, it's hard to see. This is the ESP8266 Feather Huzzah Feather board that I have basically. It's the typical ESP8266 board, and then connected to it on the top is the PCA9685 servo PWM driver feather wing. And again, I've done a little video on this. This is great little feather that you can use to connect a servo like I have right here, just a little hobby micro servo. And then connected to it right here, this is just a battery power supply. This is a 4 AA battery power supply. And it's plugged in right here to the PCA board. That's just because your servo typically needs a more powerful power supply, because when a servo gets stuck, it can pull like up to an amp of current, and you don't want to pull that through your USB port there. So you usually want an external power supply, and these feather wings make it really easy. You just connect the external power and you're good to go. Now, what this thing does, and again, you can go back and check out the video that I've done on how to actually use this, but it's basically a PWM, a pulse width modulation driver. So it has 16 channels, although the feather wing only, I think, has 8 channels broken out on it. And each of those channels can have a pulse width modulation signal sent on it, and each one can vary. Pulse width modulation is basically when you turn a signal on and off really fast. So you can use it to simulate an analog signal. For example, like if you wanted to take an LED and make it half as bright. So normally if you want full brightness, you just have a digital I/O line and you turn it on and it's fully bright. You turn it off and it's completely off. But if you want to go halfway, you can use a PWM signal where if you turn it on and off really quickly, and if you kind of control how often it's on versus off, you can effectively get an analog-ish value. It's not technically analog, it's not, you know, exactly half the voltage, but if the signal changes fast enough and if your devices don't care about how fast they change, then they effectively see it as a halfway voltage there. And that works great for like dimming an LED, so controlling the brightness of an LED, or for talking to a servo, because again, if you go back to the previous video I've done on this, and there are actually some great guides I think that I linked to that talk about how servos work, you need to send a very specific pulse train to the servos that tell it basically what position to move into. And so again, you just control how often that signal is on versus off with a pulse width modulation signal, which is great for this PCA driver board because it can generate 16 independent pulse width modulation channels, so you can control up to 16 servos. And you can control servos from your board directly, especially from Arduino and even MicroPython, because you can generate those PWM signals yourself, but you're usually a little more limited in that you probably have to have either your program needs to be really simple because it's going to be generating those signals, or you need to mess with timers, look at some of the advanced hardware on your chip. And then even then, you've probably got to deal with, well, the power supply for your servo. You don't want to power it from your board. So again, these little PWM drivers make things a lot easier for connecting to a bunch of servos. Okay, so like I said, I'm going to jump through real fast the usage with CircuitPython for this driver. And I have a guide. This is the link to the guide that shows how to use it with MicroPython. We're working on updating the guides right now. So for now, again, remember, this guide shows how to use it with MicroPython, but I'm going to show how to use it with CircuitPython. And then eventually, pretty soon, this guide is going to be updated to also just describe how this works with CircuitPython. But you can watch this video and follow along. And the differences aren't that great. It's just basically installing a different library, and then using it is pretty much the same. So, okay, so to use this then with CircuitPython, so I've already got my board loaded up with the latest version of CircuitPython. That's the ESP8266 board, but this should work on the SAMD21 board. Just be aware, we're working through some trickiness with copying files to the SAMD21 right now, especially if you're on Mac OS X. It likes to create these trash files, and if you're on a board that doesn't have an external SPI flash, which has a bigger file system, you can run into some tricky issues. So we're working on some ways to solve that. But for now, I'm going to use the ESP just because it has a lot of space and it's easy to use. Okay, so to use this driver with CircuitPython, one big difference, I need to install a couple extra modules. So let's see, I'll show you also, so the code for this module for the PCA9685 driver for CircuitPython, it's up on GitHub. I'll put a link to this in the description when this goes up on YouTube. And this is the new code for this. And then I'll also put a link, this is the old code. This is the MicroPython specific code, which will work on the ESP8266 still because it has the machine API. It has enough space for that. But again, this is all about CircuitPython here. Now you might notice immediately there is a difference in this driver. It's a module, so it is a folder at a top level, whereas the older driver is just a bunch of .py files. And I showed in the previous guide and video, basically you go to the releases and you grab these .mpy files, and then you individually copy these onto your board, and then you can import them. Works fine, but it gets a little annoying because if you have a lot of different drivers, you're gonna have all of these .mpy files in the root of your board, and it gets a little trickier and annoying to manage all those files. And if multiple drivers happen to have a file with the same name and they conflict, then you're really in trouble because how do you make them both work? So going forward with CircuitPython, we've switched to a model where all of our drivers are going to be based on modules in Python. And a module is basically a folder that looks like a library you can import. So just like in Python, you can import a .py file, or in MicroPython a .mpy file, and that will give you access to the code inside of it. You can do the same thing with a folder, and I've talked about this before. You basically just have to create a folder, and you put this underscore init.py, and that's a magic thing that tells Python, treat this folder as a module so that code can import it directly. So if you copy this folder, this PCA9685 folder, to the root of your MicroPython board, you can import Adafruit underscore PCA9685 as if it was a .py file. And MicroPython and even normal Python will look inside that directory, see the init.py and say, oh, okay, this is a module. And then all of the files inside of there are accessible. So you can access, as children of that module, these different subfiles here. So inside of this class or this driver, I have pretty much the exact same code, but I'll show you some of the differences when we get a little further along. But I have the same kind of structure. There's a motor driver, the PCA9685 driver, a servo kind of class, and a stepper motor class that help use those different types of devices here. So that's one big difference, is that now with CircuitPython drivers, they are modules, which means you need to copy folders to your board. So that's been a little tricky in the past, but I updated AMPI, the tool that you can use to copy files between boards, at least boards using the serial REPL, and I added some extra commands, and I mentioned these I think in the intro to CircuitPython video, but I'll show them real quickly how to use these commands. So you can actually copy a folder in one command with AMPI now. You can also delete an entire folder, and that will copy the folder and all of its children, or delete the folder and all of its children. Okay, so we're going to need to get this driver onto the board. And basically, again, if you go to the Releases tab, you should see there's now a zip file for all of our drivers. So if I download this file, it's going to download the zip file. If I open up the zip file, it's going to extract it. And then if I go to my downloads here, oh, come on, open up. There we go. So now you'll see it just downloaded a zip file. Inside that zip file is a directory, and then inside that directory is the set of files, the .mpy files and the init.py file inside of there. So I need to download that, and then I need to get that directory onto my board. And so I'm going to use the ampy put command, and make sure to upgrade to the latest version of ampy. So if you don't have the latest version of ampy, it should in theory be as simple as a pip install pip install Adafruit -ampy --upgrade. Very critical. You have to have this -- upgrade to tell the pip tool to upgrade your current version to the latest version that's on PyPy, the Python package index. On some systems, like on Linux, you might need to run with sudo. On Mac OS X, you might need to run with sudo unless you're using homebrew Python, in which case you don't want to run with sudo. It's a bit of a mess, unfortunately, in the Python world. So you kind of need to know, if it doesn't work without sudo, try it with sudo, and it'll probably work. And on Windows, you don't even need sudo. So I wish it was simpler in the Python world, but it's not. So that's a little bit of a complexity there. Anyways, though, make sure to upgrade to the latest version of ampy, and just to double check, if you run help, you should see the rmdir command. That means you have the latest version with that extra command. And then I've also set the ampy _port environment variable, and I'm going to set that to the serial port of my ESP8266 Feather. That way I don't have to specify the port every time I run ampy commands. So now I can run ampy ls, and this just lists all the files, and you can see I only have a boot.py, which doesn't really do anything right now. So there's nothing on this board. Okay, so let's copy this folder that I just downloaded. So I'm going to do ampy put, and it's from my downloads directory, the Adafruit PCA9685 folder. And I'm just going to give the folder name, and then what ampy's going to do is it's going to copy that folder and all of the children inside of it. So if there are subfolders, it's going to copy all of those. If there are sub-files, it's going to copy all of those. And you can see it took a little bit longer than most ampy commands just because it's going through one by one to copy them. But now if I run ampy ls, you see now there's a folder on here, although you can't really tell. Maybe in the future I need to add, does it say file or folder? But I can also say ampy ls, that Adafruit PCA9685 folder, and we should hopefully see, yeah, here's all the files inside of there. Okay, so that's cool. Now there's a couple extra things that I need to copy over before I can use this driver. And again, this is something you'll see with all of the CircuitPython drivers. There are two dependencies that most of the drivers have. So there's a dependency on something called the bus device module, and I'll put links to this GitHub repository in the description below. But this is another module. It's kind of a driver in some ways. And we'll come back to what this thing does, but this is a dependency of the PCA9685 driver. And then there's another one called the register module, the CircuitPython register. And again, this is a dependency that the drivers use to simplify how they work. And we'll dig into more of these in a moment here. So I need to download these. Again, go to the Releases tab, grab the latest release.zip file, open it up. You'll find a directory inside of there, like Adafruit Register, and you need to copy that onto your board. If you're using like a SAMD21 board with a file system that's mounted over the USB drive, you can, in theory, drag and drop. But again, like I mentioned, there's some issues right now with Mac OS X and some of the trash files and temporary things it creates. But anyways, I'm going to copy these. I'm going to put these files on my board. So I've already downloaded them in my downloads directory. I'm going to copy over the Adafruit _register. So we'll copy over that, and it just takes a second. And so the register class, this is kind of interesting. This basically simplifies how you access the registers on the device. So when you're writing a driver, for most hardware, you're just interacting with the registers on it. So this PCA9685, it has a register or a bit of memory that controls the PWM signal for each of its 16 outputs. So really all that the driver does is just set some registers to say, set the frequency, maybe set some mode and some initial state, and then when I say I want to move the servo to a certain position, that translates into a certain PWM frequency and duty cycle that needs to be set, which just translates into a write to the registers that control the duty cycle and the PWM frequency for that. Okay, so we copied over the register. Now let's copy over that bus device that I talked about. So Adafruit _bus device is the other module that I need to copy over. And in the future, once we have boards that are shipping with CircuitPython, you might not even need to do these two steps because we're going to bundle in a bunch of these drivers out of the box with them. So you'll probably have these on the boards already. But again, this is a little bit more of an advanced video, so I'm kind of showing folks the current state of what you can do. Okay, so all of those are copied over. So I'm going to go into the PCA9685 repository. I have that synced locally on my machine here, just because I have a little example script inside of there. So we'll look at this example. So this is from the GitHub repository with the PCA9685 code, and I have a little examples folder, and there's a servo example that we'll look at here. So this basically just moves the servo that's connected to channel 0, which is what I have connected right now. It just moves it between the two extremes. And it does that using the position function on this servo class. This class is exactly the same as the MicroPython compatible driver that I've done a previous video and guide on. Again, like as I've ported these drivers over, I've left the interface exactly the same. It's just some of the setup, like right here, that differs between CircuitPython and MicroPython. But the usage down here is exactly the same between these. So this just changes the position, and it's using the percent or the amount of time that the signal is on versus off, if I remember correctly. And so this is basically in microseconds. So 1,000 microseconds on, then that basically means that you're going to move the servo to one extreme. 2,000 microseconds to the of a signal on, we'll move it to the opposite extreme. So it's a weird way that servos work, and it's kind of because they have this certain feedback mechanism with potentiometer in there, you're kind of controlling things at a low level. But if you go to the guide, there are actually different ways. You can specify in degrees what position you want, like 180 degrees or 90 degrees. You need to know a little bit about your servo to set that up, though, because each servo has a different range of motion and things like that. So that's why I like to use this period in microseconds here to get that. Anyways, so let's run this code. So I'm going to use the ampy run command, and I'm going to run that example, and this is the servos example, so servo.py. So I'm going to run that, and notice that my servo is moving. So the way this code is working, you can see I just have an infinite loop, and I move it to one extreme. I pause for a second, time.sleep 1 second, and then move it to the second extreme and pause for another second. So you can see it's just moving and pausing as it goes here. And then to stop this, what I'm going to do is I'll use the ampy reset command, which just resets the board, so it just stops the script that was running there. Okay, so that's how this works, and so that's all you need to do if you want to play with the PCA9685 with CircuitPython. Just copy over those two modules and then the PCA9685 module, and take a look at the example code, and you can kind of get started and see how this works. Now, I'll just briefly mention too, like what is different between the MicroPython compatible code versus the CircuitPython compatible code. It's really just this setup right here. So ultimately, I need to get an instance of the I2C bus and pass it into the servo class. So like this code is exactly the same as the MicroPython code. It's just this code that differs, and that's because if you go back to the intro to CircuitPython video, I talked about how we have a board module that gives you a little bit easier access to some of the pin names and things like that. So this SCL and SDA pin are a little bit simpler and more straightforward to access from this board module. And then we also have explicit bit-banged I/O versus native I/O for like I2C access or SPI access. And so this right here is kind of picking. For the ESP8266, I have to use bit-bang I/O because the ESP8266 doesn't have a hardware I2C interface, whereas other boards might have a hardware I2C interface, and so that's where this native I/O interface comes in. So if you're using on the SAMD21, you could use bit-bang I/O. That's implemented and available on the SAMD21 boards, so you could use any two GPIO pins, or you could use your native I2C interface and just uncomment the bottom line and comment this top one. And then you'll get that to work, and it should, in theory, just work out of the box because the SCL and SDA pins from the board module, we map to the pins that make the most sense. So on the feathers, we have labeled SCL and SDA pins, and so the pins that you import from the board module will match the labeled pins there. So most things don't need to change when you're using or when you're changing which boards you're swapping between here. So okay. That's how the code works for this, and then it just creates an instance, of the servo class. It's exactly the same as the PCA9685 driver, and the usage is the same like I mentioned here. Okay, so let's look at the driver code and look more at the differences between these. So I'm going to go and let's look at the MicroPython compatible driver code. So let me just find real fast where I had that. Yeah, so this is the repository for it. And let's look at this PCA9685.py file. So This is the MicroPython driver. This is the same driver that's mentioned in this guide right now. And we can kind of see how this thing works. Like I mentioned, talking to a little I2C device like this, it's really just talking to the registers on the device. And in fact, I think I had, let's see, we'll do PCA 9685 datasheet. So if we look at the datasheet for this thing, it describes all of the registers on this device. And like I said, there's just a table, I think it's like 15 or 16 registers, or maybe a few more than that. Pretty much every datasheet is the same. So most datasheets have a big table of every register, and each register usually has an address, like how you reference that register. It's usually like an 8-bit value or something like that. So this is showing, here's each of the registers, this big table. So the registered address 0 is your mode 1 register. And then later on in the datasheet, it'll explain register by register exactly what it means and like what each of the bits inside of this register means. And so very, very handy, especially if you're writing your own driver. You're going to look at the datasheet and be looking at a lot of these registers. So if we look at the code for this in the MicroPython driver, that's really all that the driver does, is access those registers. So in the initializer, it needs to take the I2C bus so that it knows how to talk to the I2C bus. And then it saves a reference to that. And then the address, it needs to know the address of the device, because each I2C device can have a separate or a unique I2C address for it. And then it has a few high-level things like reading and writing, where you can read and write a register value. So this just reads and writes an 8-bit register given the address of that register. So, like address 0 for the mode 0 register, or address 8, for example, would give you the LED 0 output byte 2, like the low order byte for that. So that, you can read and write the values. And then all of the functions in this PCA 9685 class, like setting the frequency, for example, right here, it's just using that read function to read the current value of, for example, like the frequency register. And then it's maybe doing some math to figure out, okay, the user wants a new frequency, and so I need to do some computations, because you're going to need to look at the data sheet and see how this device expects to have the frequency set. It's probably using a certain fixed point math or something like that, and so that's what some of this stuff is happening, or what some of this code is doing. And then it's just writing to these registers. So you can see these write commands are just writing, like this is writing to the mode register, the registered address 0, and it's writing this new value to it. And then, this next one is writing to the prescaler register, so the registered address OXFE. So again, if I go back to the data sheet, if we go all the way down, you can see the register at, keep going. Here we go. So the register at address FE, this is this prescaler output, which just kind of changes the scale of your PWM output for this chip. So again, that's all that this command is doing. It's just setting a register. Now, the unfortunate thing is it's not very easy to understand what this code is doing, though, because everything is happening at a very low level. It's interesting in that, you've got low-level access. I can write to any register. I just give the address and I'm good to go. But, as a driver writer, it's not really obvious to me that these 3 lines are setting the mode, setting the prescaler, and then setting the mode again. It's obvious because someone happened to comment this, which is a very nice thing to do. But if you just saw this write of OXOO and, what is that thing? I've got to go back to the datasheet and figure that out. So that's a little bit, I wouldn't say problematic, but it would be nice if this was a little more descriptive. And just looking at the code for this, I could say, set the mode register to this value, or read the mode register and give me the current value of it. So we'll look in a moment here how maybe you can make this that possible with some of the CircuitPython stuff, like the register module that I was talking about. And then I won't get too far into setting the PWM frequency and the duty cycle. These again are just setting registers. Like the PWM function is actually the core function of this module. It just writes to these PWM registers that the chip has. So for each of the 16 channels, there's 16 bits of PWM output. And so you can set the high and the low order bits or bytes for that. And that's exactly what this function does. It's using the struct module to pack and unpack these 16-bit values and set them. But that's really all it's doing. It's just setting those 2 registers inside of here. And then everything else in this module is built on top of that PWM function. So setting the duty cycle is actually just converting a percent duty cycle, like 0 to 100%, into a PWM value that goes from 0 to 4096, like a 12-bit value inside of here. So this duty cycle function doesn't even set any registers. It just calls this PWM function. And then another higher level abstraction on top of that, the servo class inside of here, it's built on top of that PCA9685 class we were just looking at. You can actually see it creates one internally. And then when you call the position function, it just figures out what duty cycle do I need to set, and then it just calls that duty cycle function, or actually here it calls it right here. So it doesn't even set registers itself. It just figures out, oh, you want to move the servo to position 90 degrees. Oh, well, that's a 50% duty cycle, for example, and then it computes the math or figures that out and then calls the duty cycle function, which calls the PWM function, which sets the registers for this. So it's kind of nice in that all the high-level stuff is built on the low-level stuff, so it's just a few low-level things that you need to change to make this driver work with CircuitPython or something else. Okay, so let's look at the CircuitPython version of this driver. So we'll go back up to the top, and again, remember, it has a folder now. It has a module, so there's this init.py, which is empty. That's kind of the convention in Python. If you have an empty init.py, that just tells Python this is a module. But let's look at that PCA9685.py file. And it's going to look a little bit different. So you'll notice, for example, I'm importing that Adafruit register and Adafruit bus device module, and I'm actually importing a few things that are inside of there. And so we'll talk more about these in a moment. And then the PCA9685 class, now I have these things at the top here. And so these are actually how I'm defining registers as a high-level member of the class. Because what I can do now is actually interact with these registers by just interacting with the mode register as a property of this class object. So now I don't have to do these low-level reads and writes. You know, for example, if I look at setting the frequency here, you know, these three writes are kind of confusing and weird, but if I look at the updated driver, here's the frequency function. Check this out. So setting that mode register and setting the prescale register, I'm actually just setting them as if they're a property of this PCA9685 object. So my mode 1 register, I'm setting to a new value that I'm computing. This is exactly the same as this line right here. And in fact, this value that I'm computing is exactly the same. It's just changing some bits inside of the mode, puts it into sleep mode, which I think you have to put the chip to sleep before you change the prescaler. But you can see how this is nice in that it's a little bit more obvious now that I'm controlling the mode register. I'm setting the mode register to a new 8-bit value that I'm computing right here. And same exact thing with the prescaler register, and then the mode register when I set it back to the previous mode. And you can also see, like, when I'm reading the prescaler register right here, I'm just reading it as if it was a property value, this self.prescale_register. Compared to the old driver, I had to call this read function and give it this cryptic address. So, you know, it's not as immediately obvious to me what's happening here. Whereas right here, it's like, oh, okay, I'm reading the prescale register for this device. So that's what's happening. And that's, I think, a pretty powerful abstraction as a driver writer to think about. So that now, instead of looking at the code as, okay, I need to read and write to these addresses, I'm thinking it more of, I need to model the registers on this chip in my class, and then I just interact with it and I write the code that controls those registers. So when I want to set the PWM frequency, I know that, okay, I need to go and change some of these PWM registers. And you can actually see the way that this works. So for each of the registers, I define it as a class variable. And this is a little bit of a different Python thing. So in Python, there are instance members. So when you create a class in your initializer, anything that you refer to on self dot, it's like self.i2c device. This is an instance member, which means each instance of this PCA9685 class has a separate self.i2c underscore device instance. So it just means that you know, each of your PCA9685 classes might be talking to a different I2C device, because you know, you might have multiple of these boards connected. As long as they have a different I2C address, you can do that, but each one needs to have its own I2C device instance inside of here. Whereas these class variables or class members are kind of global to all of the PCA9685 instances. So this just means that, for each instance of this PCA9685 class, it doesn't have its own copy of this mode 1 register object or this prescale register object. There's just one copy for all of the class members. And we can do that because the way these classes work, they don't care about which device they're connected to. They just know when they're talking to an I2C address, or when they're talking to an I2C device, they just know that there's a certain interface for talking to that device, and they trust that the object, the instance that they're connected to or associated with, has a specific device that they can talk to. And it might make a little more sense as we dig more into this class, but that it's a very important difference here that things that are defined under the class like this are class variables. So you might think of them kind of as static members, although there is an explicitly separate static member type in Python, which I honestly forget some of the differences why. I'm sure there's some esoteric differences, but just think of it as a static member if you're used to that in like the C++ world, where there's just one instance of this object for all of the classes, versus anything that refers to your self dot. These are instance members, so there's a separate one of these for each of the instances of your class. Now, you can see I'm modeling these registers, so I'm creating instances of this I2C struct module, which is from this Adafruit register module. Inside of there's a unary struct class that I'm creating, and then there's also a struct class that I'm creating here. And this PWM register thing, this is just a tuple of multiple registers. So I just made a collection of registers because, like I've said, there's 16 PWM channels, and so each of these represents the different PWM channels for this device. And so we'll look at these in a second, but before I dig into this register class, I just want to take a quick detour and talk about this bus device class first. So the bus device is maybe one of the first kind of important differences or interesting things that we're trying with CircuitPython as a driver writer. And so what bus device does is it basically represents access to a bus, like the I2C bus or the SPI bus. And a bus is just a communication protocol or communication system that you can have multiple devices connected to. So for example, I2C, you can have a bunch of devices connected to your I2C bus. They all share the same clock and data lines. And then the I2C protocol just has a certain way to control those clock and data lines where each device can individually talk to your board. And there's an addressing scheme that they use to talk to the right device. Whereas with the SPI protocol, it uses like explicit digital input lines as a chip select line. So you set a line high or low that says, hey, I'm going to talk to this chip, and then there's a clock and a data and input output lines that are controlled for that. Now the tricky thing is, and Arduino actually ran into this problem, what happens when you have multiple devices on the same bus, but they each need to control the bus in a different way? And a good example of that is with the SPI protocol. It has all kinds of different ways that you can control the clock. There's a phase and a polarity and even the speed of the clock that differ between devices. So talking to a little micro SD card might have a completely different phase and polarity and clock speed compared to talking to like maybe a little SPI pixel that you can control, like an RGB pixel that uses the SPI protocol. And so the tricky thing is, like, what happens when you're running code that maybe wants to light up a little pixel that's on a board and also talk to some SPI flash or like a micro SD card or something like that? Your code needs to change between those modes. So it needs to say, okay, I'm going to light up the pixel, so I need to change my clock speed to this, and I need to change my polarity to this, my phase to that. And then when I'm done, I need to make sure, before I talk to the little flash chip, that I change my clock speed and my polarity and my phase to match what my flash chip needs. And you can do that. You can write all that code. You just need to be very careful, because as soon as you forget to do that, you're going to mess something up where you're going to set your pixel color, forget to change your clock speed back to whatever your flash chip needs. You're going to try to talk to your flash chip, and it's going to be confused because it's not going to get the right speed or the polarity or the phase. It's not going to work. You're going to scratch your head and wonder what's going on, and then that's a really tricky and annoying bug to track down. So wouldn't it be nice if you could remember somewhere that when I talk to this device, I need a certain speed or polarity or phase, and when I talk to another device, it has a completely different speed or polarity or phase. And anytime I talk to those devices, programming languages are smart enough, like just set that speed and that polarity and that phase for me. You know, you've remembered it, so do that so that I don't have to do that, which just saves me from myself so that I'll never forget, because the compiler is smarter than me, or the programming language is smarter than me, and it knows every time I access that thing, it can make sure that it's set the clock speed and the polarity the correct way. And so a good example is on like this Metro board, this Metro Express board. This is a new board that'll be coming out soon. I think we've done a whole bunch of little desk ADAs and things on this. This has a little SPI flash chip embedded on it so it can have a bigger file system for MicroPython. And then it also has a little pixel connected to it that also uses the SPI protocol to control it. But the problem is, when you're trying to share both of the devices on the same bus, we have to be very careful to make sure that you're using the right clock speed and polarity. So this bus device is an abstraction on top of different serial buses like I2C and SPI to let you say that I have a device that needs a certain protocol for using this bus. And then it uses a cool thing in Python called a context manager. So if we look at, and I'll put links to this in the description when this goes up on YouTube. This is the Python extension protocol or proposal that added this with statement to Python. And so the with statement, and I think hopefully they have an example in here. Yeah, the with statement is basically a way to make a block of code where you can say, okay, anything that runs inside of this block, before you run this code, I want to insert some extra code that you run before and after. And Python will guarantee that your code runs before and after this. And so this is, you might see this a lot with file access. So like a with statement to open a file, for example, will open the file, and then your code will run and it can access that file. And then as soon as your code finishes and you go to the next block, that context manager will close the file automatically. But the cool thing is Python realized that, you know, there's a lot more than files that you might want to do this with, and you can define your own context manager. And the way that you do that is using this enter and exit function. And so this is the bus device module code. And if we look at this, for example, in the SPI device module, it has this underscore underscore enter and underscore underscore exit code. And so what this code does is it actually will set the SPI bus speed and chip select and polarity and phase. So you can see it configures the SPI bus. It'll actually set the chip select line also, so you don't need to worry about doing that. So it will set your chip select line false or as low, because for most devices they're asserted low. Maybe in the future we might see some other devices that we need to tweak some of this to work with. But anyways, you know, it'll do that when it enters the context manager, and then when it exits the context manager, it will it'll set your chip select back to the unselected value, which is usually a high value. Usually chip select is active low, and then it's done, and it will give the SPI bus back to whoever wants to use it. And so that's kind of nice, and that now, yeah, and you can actually see some of the usage in this comment right here. So it just shows, okay, now when I want to use this, so if I create an instance of this SPI device class, which is what's being shown right here, I can use it as a context manager. So when I say with my device as SPI, so this just says use this context manager. So when Python gets to this with device as SPI line, it's actually going to call this enter function, because at the very start of this block, it makes sure this enter function is called. That's going to configure my SPI bus however I've set it up previously. And you know, I set my SPI bus up ahead of time right here in the initializer. Basically, I set like the chip select and the speed and all of that. And then I can use this SPI device object, and I can, you know, read and write bytes from it. And I know for sure that the speed has been set correctly, and the polarity and the phase and all of that is all good. And then as soon as this block is done, the exit function is called, and it's finished. It's done using that device. So this is really handy, because now I can write code that uses a SPI device, and I don't need to worry about what might have been using the SPI bus before this. I can use this SPI device abstraction and just say, when I talk to this device, I need this speed and this polarity and this phase. And then if I use it as a context manager, every time I do that in my driver, it ensures that I've got my SPI bus set the correct way. And so there's also an instance of this for the I2C bus. It's not as interesting for I2C just because usually your devices all share the same kind of like speed, and like I2C doesn't have as many differences. But in CircuitPython in general, we have this convention of locking the bus before you use it. And that's, if you look at the code for this, you see this try lock and a little spin lock right here that will lock the bus. And again, this is just to ensure in CircuitPython that things that use shared buses get exclusive access to that bus. And so that's why we have a concept of this locking. And then to make it easier so that you're not constantly having to manage this lock yourself, that's what the bus device module does, is it adds an abstraction on top of that locking so that instead of messing with the locking at a low level, I just mess with a SPI device that uses a certain speed or polarity or phase. And using context managers in Python, it makes it really easy. I don't even need to worry about all that locking stuff. I just write in my code, I'm going to use my SPI device, and then beneath the scenes, the bus device module here will do all that locking for me. So that's something that we'll see internally in a moment here. But back to that PCA 9685 class. So, we see all this register access inside of here. And so let's look at this register code. So again, remember this register code, I added this model of registers to simplify accessing the registers in my driver code. So let's see how these things work. And I'll give a link to this repository. This is the CircuitPython register module on GitHub. And so let's take a look at some of this code inside of here. So again, this is a Python module. And inside of here, there are a bunch of little sub-modules that represent different types of registers. And over time, we're going to add a lot more to this module. But let's look at like the I2C struct.py. And so inside of here is where I define that struct and unary struct class that I use right here. And so the way that these classes work is that they represent a register that has a certain address. And so that's what this first parameter is. And then it uses the Python struct module, or in MicroPython, it's the microstruct module. And the struct module is super handy. If I just search for struct module, it should be the first hit. Yeah, it's from Python. This is one of the coolest things. I love this in Python. It's the same in Python 2 and 3 pretty much. But if you're doing embedded stuff, you're going to love this module because basically it lets you represent, or lets you talk to, not even necessarily talk to, but it lets you take certain values and pack them into bits of memory that use C-style types. So things like an unsigned 8-bit integer, or a signed 16-bit integer, or a 32-bit floating point value, or a 64-bit double precision floating point value. In Python, you don't deal with those low-level types. You just deal with a number that can be an arbitrarily large integer, or a floating point value, for example. You don't care that this is like a 32-bit value. Whereas when you're talking to little devices like this, on this PCA 9685, each of those PWM registers is a 16-bit unsigned, if I remember correctly, value. And so that's an important difference because a number in Python isn't necessarily a 16-bit number. So when I take that number in Python and try to send it to my device, something needs to know that that number has to be converted into a 16-bit value. And it is important because if that value is larger than 16 bits, it needs to overflow in a certain way that like C code would perform. So the struct module is super handy in that it lets you take a Python type, like a number, and pack it into or unpack it from a more traditional C type or a bit of memory that uses C types. And like this table right here kind of tells you, so the way that this module works is you give it a format string. So you give it a string, for example, you can see right here, this less than B. And this basically means the first thing, this less than, is a little modifier that says the byte order. Because remember, if a value has multiple bytes, different processor architectures have different byte orders. So there's like big endian and little endian, which just changes. If you have a 16-bit value, should the low 8 bits come first and then the high 8 bits? Or should the high 8 bits come first and then the low 8 bits? And that's different, big endian versus little endian. There's even network byte order, and so there's lots of differences here. But that's important because when I talk to this device, it has these 16-bit values, and they need to be in little endian byte order, because if I got it wrong, if I did big endian, the bytes are going to be swapped, and I'll get the completely wrong value for that. But that's the cool thing about the struct module is I can just tell it, if I put this less than, whatever it sees beyond this, just treat, if it's a multi-byte value, treat it as a little endian value. So that's nice. And again, it's nice in that I read my data sheet, I see these are little endian registers. It's super easy to represent that. I don't need to monkey around in the code and manipulate these two different bytes. In fact, if I look at the old code for this, it's basically, well, actually, it's using the struct module also here to do that. So, but in a lot of drivers, you see it's actually interacting with those two bytes independently and ORing them together, and it's kind of messy. It's kind of annoying. And so that's nice that you use the struct module to do that. Now this uppercase B, this then is the type of value. And so if I look at this unsigned character, it's basically an 8-bit value that can go from 0 to 255. And so that's what I'm representing here for this mode register. And so again, if I go back to that data sheet, you can see the mode register is an 8-bit value way at the top here. So at address 0, it's an 8-bit value, and each of those bits means a certain thing. And so that's what this is representing right here. So this I2C unary struct, which just means there's an 8-bit register at address 0. So it's address 0, and then the format string just says that this is an unsigned 8-bit value, a capital B struct value. Now the cool thing is this unary struct class will take care of talking to your I2C device and the register you provided at the address, and it will convert between that format for you automatically. So that's how I can set, for example, right here, self.mode1_register equals the value 0x00. This will automatically convert the value 0x00 to an unsigned 8-bit value in little endian byte order, although it doesn't matter. If it's a single byte thing, endianness doesn't matter. But it'll do that conversion automatically using the struct module, and it will write it out to the address 00 on the device that I've associated with this I2C device here. So that's pretty cool, and that's how it simplifies the driver now, so that I don't have to do those reads and writes individually. I'm just interacting with these registers as properties of this object effectively for this. So we can look at the code for this. I'm not going to get too far into the code for this because it uses this kind of advanced thing in Python called a descriptor. And a descriptor is like a property because what's happening here is, I'm interacting with this as if it's just a variable or a member of this class. And just like the code above right here is setting this I2C device variable to a value of this class instance, this code looks the same, but actually what's happening is it's a property or a descriptor in Python. So there's some code that's running every time I set this value, and every time I get this value, a separate bit of code runs. And that's actually what this get and set function do right here. So whenever I get and set that property value, these functions are called. And you can actually see what these things do. They're using a context manager, which is using that bus device that we just looked at. So it's taking that I2C bus and using it as it's assuming that it has a bus device instance. And then it's using the context manager using the with statement right here. That's going to do all that locking and unlocking for you. And then it's just accessing, it's doing like, here's writing to some of the memory. And then here's reading some of the memory from it. And it's just doing those low-level read from and write to operations, exact same operations that we actually saw in the old driver. So like, here's a write function, and the write function is just using this write to memory and read from memory functions. We see similar functions in this register class, writing to and reading from the memory right here. But it's doing that automatically for me anytime I'm getting the value. And then once it reads the value from the I2C device, it uses the struct module to unpack the data and do that conversion, into like, do I want an 8-bit byte or maybe a 16-bit value? It handles that automatically for you. So that's kind of the magic here of how we model the registers as class instances. And then once I have them modeled as these class instances, and I'm modeling them based on the struct module, which gives me a lot of freedom to talk to all kinds of different data types, and I don't need to worry about doing those conversions. The struct class is going to do that automatically for me. And then in my driver code, it just becomes a matter of accessing those registers as properties right here. So this is really cool and really powerful abstractions as a driver writer. Now, I should say this doesn't come for free. There is some overhead to this. Each of these struct instances takes a little bit of memory. But that's something that we're exploring with CircuitPython because, again, remember, with CircuitPython, we really want to focus on ease of use and making things a little bit simpler. So we want to explore this trade-off of, let's spend a little bit more memory to store this register instance as like a class instance. So, a few bytes of memory it will take up. But the benefit is that my code is a lot simpler and that, it's easier to look at this and say, oh, yeah, I'm interacting with the registers on this device. And let's say I wanted to add a new register to talk to. So I look at the data sheet and I see, there's like, I think at the bottom, there's a few kind of random registers, like this test mode register. If I wanted to mess with this register, I can look at it and see, okay, at address 255, there is a readable and writable 8-bit register right here. So if I wanted to add this as a register, it's just a matter of adding that as a class instance here. So we'll say maybe the test register equals an instance of the I2C struct module, and then I'll say the unary struct class at address OXFF, and we'll say this is an unsigned 8-bit value, and so this is the test register. And now I could interact with that test register if I wanted later on in my driver code. So super handy, really cool thing that I think will simplify a lot of the drivers, because now when you write a driver, it's more a matter of defining the registers in your class, and then writing the code to interact with those registers. So kind of cool abstraction. One thing maybe I forgot to mention too, what's the difference between unary struct and struct? They're very similar. If you look at the code for these, the struct class just gives you access to the raw struct values. So when you use that struct module in Python, like I was mentioning here, it has a pack and unpack function. When you pack a value, you have to give a tuple, which is like a collection of values. And when you unpack a value, you get a tuple back, even if you only have one value inside of that struct. So, even though for this mode register struct, there's just one byte inside of here, if I use the struct unpack and pack functions, I have to set a tuple. I have to send a one value tuple to it to set that value. Which is a little bit ugly, because in Python to send a one value tuple, you actually have to give the value, like let's say, if I'm setting self.testRegister, I would have to set this to the value like 100 comma. So this is a tuple with one value. You might think like, a tuple with two values would be something like this, like 100 comma 200. That's two values. Like, think of it like an array. One value looks like this, and you have to have this comma and the empty kind of parentheses, because if you had this, Python is confused. It doesn't know whether you mean the value 100 with parentheses to specify order of operations, so those parentheses effectively go away, or do you mean a tuple with one value? And so they erred on the side of one value tuples aren't very common, so the syntax is a little prickly and ugly. So, I could represent these mode registers as this I2C struct class. It's just ugly in that when I'm setting their values, I have to specify them using this weird syntax. So I added this unary struct class as just basically a copy of the struct class, but it does that tuple. It assumes that the struct you're using only has one value. So you can set the value directly, and in the set here, it actually unpacks that value. Well, it doesn't even need to pack it, actually. When you use the tuple pack functions, it's just you send each one as a separate parameter, but it handles that automatically. And then when you read the value, when it unpacks the tuple, it just assumes that you want the very first value, this zero subscript. So it pulls that value out and returns it, whereas in the struct class, it just returns the direct output of unpacking, which will give you a tuple. And if you only had one value, you've got to unpack that then in your code. It makes it uglier. So that's the difference here. If you're dealing with a register that just has one value, then use the unary struct class. Whereas these PWM registers, this one uses a struct format of little endian HH. And so if I go back to the struct class, we can look at H. H means an unsigned short. So that means an unsigned 16-bit value. So there are two 16-bit unsigned values for each of these PWM registers. And that's basically your on and off duty cycle values. I think it's actually a 12-bit value that the chip uses. So you set those independently. But the cool thing is I can model that as an explicit register that has two values. And so when I go down to the PWM function, you can see right here, when I set the PWM function, and here I have to do some weird syntax because there's kind of a weird quirk of accessing this setter for an array. It doesn't seem to work very well, so I did this kind of workaround syntax. Don't worry about this syntax, it's a little bit weird. But when I'm setting this, I'm passing a tuple with the on and off duty cycle values for this explicitly, and then these get packed into these 16-bit, these two 16-bit values automatically for me when I access this. So I think I'm gonna wrap up this stream then. Again, this is a little more advanced of a stream, but I figured I'd do something that's relevant to what I'm working on right now, which is porting these drivers over and updating the guides. And also, it's kind of useful because if you're checking out CircuitPython, you might be a little more advanced because it's in beta right now. So once we're shipping boards, that's when we'll probably make it a little more, we'll have a lot more guides and things out there that show you beginners how to get started with it. But for now, if you're accessing devices, check out the register and the bus device modules that I've shown in this video, because these are really cool abstractions that I think highlight some of the cool things that we're going to try with CircuitPython to simplify talking to devices. So again, remember, the bus device is the module that lets you simplify multiple devices using a shared bus. So things like SPI devices that need to change the clock speed and the polarity, you can use the bus device module, which uses the context manager syntax in Python, to control and make access to those the devices with different needs work really well and be less prone to having errors and bugs. Because if you don't manually set those speeds, then you're going to forget at some point, and you're going to get the wrong speed and not talk to your device. And then the other thing is the register module, which adds an abstraction for talking to registers in a more natural way. So setting the value of a register explicitly without having to read and write the memory with individual memory read and write commands. You model your registers as instances of these register classes, and then you just interact with those in your driver here so that you're setting your mode register or your prescaler register to the value that you expect inside of there. And so hopefully that makes things a little bit simpler to write drivers and maintain drivers and things going forward with this. So okay, if folks have questions, maybe throw them in the chat. I don't see a lot of questions because, again, I expect it's probably a little bit more of an advanced video for folks, but we'll come back to doing a lot more beginner videos momentarily in the next few weeks. Like I said, I think I'm going to do a lot of CircuitPython videos for the next few weeks as we dive into more topics for this. And also give a quick plug, next week on the 27th, that's a week from today, we will have a hack chat, a CircuitPython hack chat on hackaday.io. I'll put a link in the description when this goes up on YouTube, and to remind myself, I will actually search for that. Hackaday CircuitPython hack chat. So this is at, it's 12 p.m. Eastern, 3 p.m. Pacific, if I remember correctly. Let's double check what the Hackaday site says here. Oh no, let's see, we don't have the right link here. Now I need to find this. Here we go, CircuitPython hack chat. There we go, Google's up to date. So I'll put this link in the description. So myself, Scott, and Lady Ada and Phil, they'll be on the chat, and we'll be around just to answer questions. If you're playing with CircuitPython, you have questions, come on into the chat. I think it'll be 30 minutes. And good venue to talk to us and kind of see what we're thinking with CircuitPython. And if you have MicroPython questions, we can probably answer some of those too, but we'll try and keep this on CircuitPython. So, okay, cool. I will wrap up this stream then. We'll go back to the main shot right here. So, oh, and there's a giveaway. So we'll be giving away 5 Circuit Playground Express boards. So, hey, this could be kind of cool. So these boards right here, I don't think they'll be purple. So, but you might be able to get one of these things in the future. So tune into this hack chat. And again, I'll put a link in the description. It's Friday the 27th of January. So check that out. So also check out youtube.com/Adafruit. That's where this video and all kinds of other fun project videos will be. Check out twitch.tv/Adafruit. That's where I stream these things live. Also check out like Facebook, Periscope. If there's a live channel, we're on it pretty much. And the Desk of Lady Ada has been on fire. There's been all kinds of things going on. So stay tuned. I'm sure you'll see a lot more things there. So all kinds of fun live and video content from Adafruit in this year. Otherwise, Tony, thanks a lot for watching. Click the like, the comment, the subscribe button. Let us know that this is good content, and we'll keep it coming. So until next time, this is Tony from Adafruit. Thanks for watching. See you later.